Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like and appreciate what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can help me promote my channel to keep me going, refreshed, and inspired. And if you find my videos interesting and important to your studies, also don't forget to subscribe. Analyze the frame shown by slope deflection equations, construct the shear force and bending moment diagrams, and sketch the elastic curve. E is constant. So for this problem, take note of the moment of inertia of each segment of this frame. So it will undergo side sway, and from based on the loading, it will the whole system will rotate rightward in the rightward direction. So it is clockwise direction as shown in the figure. We will denote this side sway deflection as delta. So this is also delta by compatibility equation. So they have the same this side sway. So we will express the slope deflection equation in terms of delta. That is for both ends with moments. Moment is 2ei over L, quantity 2 theta near plus theta far, minus 3 times delta over L, then plus fixed moments. So for AB, A is the near end, B is the far end. So moment AB equals 2 times 3 over 9 L, quantity 2 times theta A, which is 0, plus theta B minus 3 times delta over L, so delta over 9, where EI is treated 1, therefore because this is 3I, so that's why we have 3 here. So MAB simplifying is a minus fixed moment, which is WL square over 12, so minus 16 times 9 square over 12. So MAB is equal to 2/3 of theta B minus 2 over 9 delta minus 108. Call that equation 1. By symmetry, we set up the equation MBA, so theta B will be doubled. So this becomes 4/3. So MBA equals 4/3 of theta B minus 2 over 9 delta and plus 108 by symmetry. The fixed moment at B, which is the right part, you just rotate the view, is positive. Then MBC equals 2 times 1.5 over 6, quantity 2 theta B plus theta C minus 3 times 0. There's no side sway or side sway displacement for this horizontal beam BC. It is just horizontal, minus WL square over 30 minus 18 6 square over 30. So simplifying, MBC is equal to theta B plus 0.5 theta C, then minus 21.6. Call that equation 3. For MCB, you interchange coefficients, then plus WL square over 20. So MCB is 0.5 theta B plus theta C plus WL square over 20. Simplifying, MCB is equal to 0.5 theta B plus theta C, then plus 32.4. Call that equation 4. Then for MCD, equals 2 times 2 over 5, quantity 2 theta C plus 0 minus 3 times delta over 5. Then there's no fixed moment, there's no loading. Simplifying, we have 1.6 theta C, then minus 0.48 delta, equation 5. MDC, on the other hand, it is theta D, that is double, but it is 0. So therefore, the coefficient of theta C will just be 1. So therefore, this becomes 0.8. So MDC is 0.8 theta C minus 0.48 of delta. So call that equation 6. Then we apply equilibrium at B, MBA plus MBC equals 0. So MBA for thirds theta B minus 2 over 9 delta plus 108 plus theta B plus 0.5 theta C minus 21.6 equals 0. Combining like terms to establish the first equation, 7 thirds theta B plus 0.5 theta C minus 2 over 9 delta equals negative 86.4. So call that equation A. Then equilibrium at C, MCB plus MCD equals 0. So zero point 0.5 theta B plus theta C plus 32.4 plus 1.6 theta C minus 0.48 delta equals 0. Combining like terms and simplifying, establish the second equation B. So 0.5 theta B plus 2.6 theta C minus 0.48 of delta equals negative 32.4. Call this equation B. So we need the third equation, and that is by statics, ax plus dx equals ax plus dx plus 16 times 9 equals 0. And let's assume that the moments are all clockwise, so that they are treated positive in the equation. So this is the equation, summation versus x equals 0. Let's just assume that ax and dx are all rightward. So ax plus dx plus 16 times 9 equals 0, or ax plus dx equals negative 144. So to derive ax, we're supposed to draw free body diagram of column A, B, and CD. So just imagine that we have MBA, which is also assumed clockwise, MCD also assumed clockwise, and they have values already. So summation moment about B, considering column AB. So we have AX times 9 plus 16 times 9 times 4.5 equals MAB plus MBA. So AX times 9, supposedly plus 16 times 9 times 4.5 in the left side, so transpose to the right side, it becomes negative, equals MAB plus MBA, which is this. Dividing everything by 9, so AX equals 1 over 9 of MAB, where MAB is 2 thirds theta B minus 2 over 9 delta minus 108, and MBA is 4 thirds theta B minus 2 over 9 delta plus 108 minus 72. So simplifying, AX equals 2 thirds of 2 over 9 of theta B minus 4 over 81 delta minus 72. Then let's have this on the next slide. This is the figure, and let's have the results earlier. These were the equations established. Equation A, then equation B, then the value, the needed equation, and we already set up AX equal to this value. Then dx times 5, considering column CD, equals MDC plus MCD. Substituting, dx equals MCD equals 1.6 theta C minus 0.48 delta from equation 5, and MDC is 0.8 theta C minus 0.48 delta, equation 6. So substitute, dx is 1/5 of quantity 1.8 theta C minus 0.48 delta plus 1.6 theta C minus 0.48 delta. Simplifying, dx equals 0.48 of theta C minus 0.192 of delta. Substitute into this equation here. So AX 2 over 9 of theta B minus 4 over 81 delta minus 72 plus dx 0.48 theta C minus 0.192 delta equals negative 144. So simplifying, combining like terms to establish equation C. So 2 over 9 theta B plus 0.48 theta C minus 2444 over 10125 delta minus 72 equals negative 72, equation C. Solving equations A, B, and C simultaneously, we get theta B equals negative 11.2976 over EI, theta C equals 67.719 over EI, and delta equals 422.5428 over EI. From here, we can now compute the moments. Moment AB is 2/3 of theta B, negative 11.2976, minus 2 over 9 of delta, minus 108. So MAB is negative 209.430 kilonewton meter. MBA is 4/3 of negative 11.2976 minus 2 over 9 of 422.5428 plus 108. So MBA is equal to negative 0.9619 kilonewton meter. Then we need MDC and MCD. MBC therefore is positive 0.9619 because of this joint. MBA is negative, therefore MBC is positive and the same value. MCD, CB is 0.5 of theta C, theta B rather, plus theta C, which is 67.719 plus 32.4. So MCB is 94.47 kilonewton meter. Therefore, MCD is the negative of this value. MCD is negative 94.47 kilonewton meter. And finally, MDC is equal to 0.8 of theta C minus 0.48 of delta. So MDC is equal to negative 148.645 kilonewton meter. Then we compute the actual value of AX, which is 2 over 9 of theta B minus 481 delta minus 72. So AX is 95.377 kilonewton, while dx is 0.48 of theta C minus 0.192 of delta. So dx is equal to 48.623 kilonewtons, also leftward. So finally, on this slide, these were the results earlier, values of AX and DX. And let's now have the actual directions for shear at B just to the left so that we can solve AY just to the right and shear just to the left to solve for AY. And these were the moments. MBC is positive, so it is clockwise. MCB is also positive, so clockwise. So shear B right times C times 6 plus MBC, which is 0.9619, plus MCB, which is 94.47, equals moment of the load 1/2 or 0.5 times 6 times 18 moment arm 2. So that this equation considers segment BC, and we sum up moments about joint C. So this is the equation, and we can now solve shear just to the right of B, which is also equal to AY if you transmit shear just to the right of B to this column. So it is also AY 2.095 kilonewtons. So summation moment about B equals 0 to solve for shear just to the left of C. So shear just to the left of C, counterclockwise equals clockwise moment. So it is equal to MBC plus MCB plus moment of the load 1/2 or 0.5 of 6 times 18, 2/3 of 6 is 4 moment arm. So shear just to the left of C, which is equal to dy equals 51.905 kilonewtons. So we are now ready to sketch the shear diagram. So remember, this is the top fiber, the outer fibers, top fiber. So since AX is 95.377 leftward, so it is treated positive 95.377, then minus 16 times 9 or minus 144, so the shear here is negative 48.623, and this distance is 95.377 divided by 16. So next is we have 2.095, very small, then minus the loading 1/2 of 6 times 18, you'll get here negative 51.905 kilonewtons. So since the x is rightward, so the shear is leftward, so it begins with negative shear. Dx is leftward, so the shear here should be rightward. So we have positive shear here, which is equal to dx 48.623. Then we have constant, and it closes because dx is leftward. And remember, this is the top fiber, the right portion. So we need this distance to solve for this area of the very small diagram there. So that's a shear force diagram. So we'll have this distance as we move on. So shear BC is, so we have to consider this intensity W at the distance x from the left. So shear BC is 2.095 minus the area of this triangle, 1/2 of x times W, where W as to x equals 18 as to 6. Therefore, W is 3x. Substitute here. Shear BC is equal to 2.095 minus 1/2 of x times 3x, and we equate it to 0 to solve for the distance here, where the shear is 0 in the calculation of area later. So x is 1.1818 meters. So as A1 is area of this very small triangular, integral of this shear equation dx from 0 to 1.1818. So integral of quantity 2.095 minus 1.5 x squared from 0 to 1.1818. So that area 1 is equal to 1.651 kilonewton meter. Area 2, on the other hand, is integral from 1.1818 to 6. This is area 2. Then quantity 2.095 minus 1.5 x squared dx from 1.1818 to 6. So area 2 is expected negative 2.095 minus 1.5 x squared dx, and area 2 is equal to negative 97.081 kilonewton meter. As I said, we have here the distance 95.377 over 16, so that's 5.9611 meters. So this distance here is 9 minus 5.9611, and it is equal to 3.0389 meters. So moment A, this is the top fiber, is AB is negative, so that's counterclockwise. This is the left, that's the right. So it begins with negative moment here. And it is negative 209.43 kilonewton meter. Then plus this area, 1/2 of 5.9611 times 95.377. This positive decreasing. Then we'll have here positive 74.846. Then 74.846 minus 1/2 of 3.0389 times 48.623, negative increasing. Then you will have here a very small moment of 0.9658. Is expected to be 0.9619, but because of rounding off of this distance, so that's still fine. Then we begin with 0.9619, then plus this area, which is 1.651, 0.9619 plus 1.651 is equal to 2.613. So 2.613 plus this area, which is negative 97.081, negative increasing, and we'll have here moment net negative 94.468. The expected value is 94.47, so that's very fine. That's okay. Then for this column, so it begins with negative 94.468, then plus this area 48.623 times 5, so we have negative 94.47 plus this area 48.623 times 5, then we'll have here 148.645. Expected is the same. So that's the moment diagram. We are now ready to construct the elastic curve. So first we have negative, it looks like that, then positive, then negative a little, negative, negative, concave down a little, then it begins to be concave up, then concave down. This is the left, right, like that, then positive. So that's the approximate, that's a bending moment diagram, and that's the approximate elastic curve. As said, it looks like this, and positive a little, then negative, concave down, then up. So that's the expected elastic curve. So that's it for this problem. I hope that you were able to follow and understand the setting up of equations and the calculations of these reactions necessary to construct the shear force and bending moment diagram, as well as the sketching of this elastic curve.